All right, let's jump right in. Today we're talking about one of the most core ideas in artificial intelligence, the hill climbing algorithm. And the best part is, to really get it, you don't need any complicated code or math. All you need is a simple story.
So let me ask you this. Imagine you're standing on the side of a mountain and you're blindfolded. Your one and only goal is to get to the very highest peak. The catch? You can't see the whole landscape. Not at all. You can only feel the ground right under your feet. How would you do it? Seriously, think about it. Because if you can answer that, you pretty much understand the whole idea behind hill climbing.
And that's the heart of the dilemma, right? Our algorithm, just like our blindfolded climber, is working with super limited information. It has no map, no bird's eye view of the terrain. All it knows is its immediate surroundings. This is what we call a local search. And that focus on the local is both its greatest strength and its absolute biggest weakness.
So let's break down the personality of this algorithm. First, as we said, it's a local search. It's got blinders on, only sensing what's right next to it. But the really crucial part is that it uses a greedy approach. And what that means is it's all about instant gratification. It always makes the move that looks best right now, with zero thought for what might happen 10 steps down the line.
So with that greedy, live-in-the-moment mindset, our climber follows one incredibly simple, powerful rule. This one rule dictates every single move it's going to make on its way up that mountain.
And here's the game plan. It's so simple. First, from where you're standing, you feel around you. You check out all the adjacent spots. Step 2, you ask one simple question. Which way is up? You find the single step that takes you the highest and boom. Step 3, you move there. And then you just do it all over again. Repeat, repeat, repeat until there's nowhere else to go that's higher. You know, the entire philosophy of this thing can be boiled down to this one sentence. All it's really saying is there a better spot next to me? Yep. Okay, I'm moving there now. If the answer is no, it just stops. That's it. It has this relentless, almost naive optimism, always assuming a better move is just one step away. But here's the catch, and it is a huge one. Our climber has the memory of a goldfish. Once it takes a step, that's it. The old spot, any other paths it could have taken, they're gone. Completely forgotten. There's no going back. No, whoops, let me try that other direction. This no backtracking rule is a real double-edged sword. It's what makes the algorithm so fast and efficient, but it's also the reason it gets into so much trouble.
Okay, the blind climber analogy is great, but let's put some actual numbers on this to see how it works in the real world. We're going to swap the idea of height for a cost value and watch how it makes a choice.
So for this quick example, we're actually going to flip the goal. Instead of climbing up to the highest point, we're trying to get down into a valley, to the lowest point. You can think of it like finding the cheapest flight or the shortest route to a destination. Here, a lower number is better, which means a downhill move is the best move.
Okay, so let's say our algorithm is starting at a location that has a cost of 5. This cost is what's called a heuristic value. It's just a score for how good or bad a particular spot is. So we're at a 5. Now we need to figure out where to go next.
From our starting spot, that 5, we look around at our neighbors. We see 3 choices. Path A has a cost of 4. Path B is a 5, which is the same as where we are now. And Path C has a cost of 6. Now it's time to apply that simple, greedy rule. We want the lowest cost possible. Well, Path C is a 6. That's worse. Path B is a 5. That's no improvement. But Path A? Path A is a 4. That's better. It's our only downhill move. So the choice is obvious. The algorithm instantly picks Path A and moves. Simple, fast, decisive.
But this is where things start to get interesting. That simple, greedy logic is great on a smooth, perfect hill. But what happens when the landscape of the problem is messy? Well, there are all kinds of traps out there, and our short-sighted little climber is about to walk right into them.
And this brings us to the single biggest problem. Our climber finds a peak, a spot where every single direction is downhill. So it stops. It takes off the blindfold and celebrates, thinking, I did it, I'm at the top. But it's not. It's only on a local maximum, a tiny little foothill, while the true highest point, the global maximum, is on a much bigger mountain nearby that it never even knew existed.
This is the classic trap, because the algorithm's one and only rule is always go up. The second it reaches a point where every adjacent step is down, its journey is over. It has no way to say, maybe I should go down for a little bit to cross that valley to get to the bigger mountain. Nope, it's stuck. End of story.
Okay, trap number 2 is the plateau. Imagine a big flat area on the mountainside. Our climber gets there, feels around, and
every single possible step has the exact same height. There's no uphill direction to take. So what does it do? Absolutely nothing. It's paralyzed. With no clear best choice, it just gives up. Stuck again.
And our final trap is the ridge. This one's a little sneakier. Think of a long, narrow crest where you can move north and south, and you keep going up. But the actual summit is off to the east. If the algorithm's allowed moves are only north, south, east, and west, it'll just keep moving along the ridge. It'll never be able to make that sideways move needed to get to the true peak.
So, when you put it all together, the local maximums, the plateaus, the ridges, you get a really clear picture of what hill climbing is. It's fundamentally simple, yes, but it's also fundamentally short-sighted. It just can't see the big picture.
It really all boils down to a trade-off. On the one hand, the pros are great. It uses almost no memory because it forgets everything, and it's lightning fast because it never hesitates. But on the other hand, that same greedy nature means it gets stuck constantly. And with no ability to backtrack, once it's stuck, it's really, really stuck. You know, ultimately, whether this algorithm works or fails often comes down to just one thing: the quality of its heuristic. Remember that? That's the function it uses to measure the height or cost of a spot. A really smart heuristic can kind of shape the landscape to help guide the climber around these traps, but a bad one, it'll get stuck almost immediately. And that leaves us with one final, fascinating question. If this algorithm is so simple and gets trapped so easily, why in the world do we even talk about it? Why is it considered such a foundational concept in AI? Well, the answer lies in its speed and simplicity. Because sometimes a good enough answer that you can get right now is way more valuable than a perfect answer that would take forever to find. And that's the simple genius of hill climbing.